My name's David Mortimer and I'm a flying instructor at Flying Time Aviation. I'm actually standing in for Noel White, who's giving this presentation this morning, but he's had to go off unexpectedly. So please bear with me, and we're going to be looking over the next half an hour, as I say, at flying IFR. That means flying obeying the instrument flight rules. So over the next half an hour then, we're going to be looking at what the instrument flight rules are, what qualifications pilots need to fly IFR, and then we'll have a look at the stages of a typical IFR flight from London Gatwick to Guernsey, I should say. And then there'll be time after for any questions that you have. So, what are the IFR rules? Well, IFR permit an aircraft to operate in instrument meteorological conditions. What we mean by instrument meteorological conditions are the conditions of flight visibility that are lower than you would have flying visually. So, below 10,000 feet for flying VFR, you need at least 5 kilometers visibility. And if you're flying above 10,000 feet, you need 8 kilometers visibility. So flying in IMC means that those visibilities are less than those quoted for VFR, and you're allowed to fly in cloud, out of sight of the surface. Except when necessary for takeoff or landing, when specifically authorised by ATC, an IFR flight should be flown at a level that's at least 1,000 feet or 300 metres above the highest obstacle located within 5 nautical miles of your aircraft. The procedures and training to become IFR rated or instrument rated are much more complex, and the pilot must demonstrate his competency to conduct a whole cross-country flight, that's flying from A to B, in instrument meteorological conditions without visual reference to the ground, except for takeoff and the final stages of landing. For flying IFR commercially then, the pilot needs to be qualified, and he needs to hold at least a commercial pilot's licence, which includes a night rating, so he can fly at night, because we don't have any VFR or visual flight rules flying at night in this country. And of course an instrument rating. So he needs to be highly qualified to fly IFR commercially, for commercial operations. So the flight goes through the various stages, and it starts with the pre-flight planning stage, which is very important. So first of all, the pilots will look at the route that they want to fly, and therefore they will then measure their tracks that they want to fly, or they will look at IFR charts and find the best possible route from A to B via airways, which we will discuss later. They will also note down the distances between each waypoint or turning point, and they will calculate the time to those waypoints, so they can keep themselves abreast of the progress of the flight. Also, they need to be able to determine the minimum en route altitudes, and the minimum en route altitudes are depicted on airways charts, or if they're planning it from a VFR chart, then they can work out the minimum en route altitudes. What we mean by minimum en route altitudes is that we're going to stay safely above any terrain or obstacles en route. And as we saw previously, we need to stay at least 1,000 feet above those obstacles that are within 5 nautical miles of the aircraft. They will then select their best cruise altitude. Cruise altitude, they want to be as fuel efficient as possible, so therefore they will go into their aircraft manuals and find out for the weight of the aircraft and the weather conditions, temperatures, altitude, etc., what their best cruise altitude will be. They'll also need to obey the airways, and some airways can be one way only, so you can only fly down them one way, and of course others you can fly one way or the other down the airway. So they have to take that into consideration as well. The next thing they look at is fuel calculations. That's very important. They don't want to run out of fuel. So from the start of the flight, they'll calculate how much fuel it takes for them, how much fuel they will burn during their taxiing to the takeoff point. Next, they will calculate how much fuel they need to take off and climb to their cruise altitude. After that, they'll calculate how much fuel they actually need during the cruise. And then they will calculate enough fuel for descent and approach, and then finally landing. Once they've calculated that, they will then calculate a contingency fuel, normally 5% of what they've just calculated, and that 5% accounts for any anomalies en route, such as the winds being stronger than forecast, or air traffic control not giving them the cruise level that they need. Aeroplanes become very inefficient if they're flown away from their optimum altitude. So once they have their contingency, then they've got to think about enough fuel if they need to divert. So they will then calculate, they will have a diversion airfield in mind. They would have already planned where they were going to go just in case they cannot land for any such reason, such as the airfield closing because another aircraft blocked the runway, or the weather conditions are below minima. So therefore they would then calculate the alternate fuel, how much they're going to need to get from their first destination to their alternate airfield. After that, they will calculate what the final reserve fuel is. What should they have left in the tanks when they land? And that's very important. They don't want to be landing with very little fuel in the tanks. There is a set minimum, and that minimum they have to calculate is for 30 minutes of flying at holding speed over either their destination airfield, if they haven't got an alternate, or their alternate airfield. So once they've calculated all the fuel, they will then make sure that that fuel obviously is loaded onto the aircraft that they require. And then it's down to the captain to decide whether he wants to take any extra fuel on top of that. And some captains just like to be safe and add another 1,000 kilos of fuel. Or they might look at the weather conditions and think, we're going to be holding perhaps at our destination for a long time because of the weather. Or maybe the traffic situation is such that they'll be holding, awaiting a landing slot. So all those kind of things go through the pilot's mind, which determines how much fuel he's going to take. They'll also check the weather. The Met Office, or the Meteorological Office, produce Met charts, and are significant weather charts, that is, for Europe, United Kingdom and Europe, and all over the world, in fact. And so they will check the weather charts for the time that they are going to be en route in order to check that is there going to be any significant turbulence en route, for example? Are they indeed going to be in cloud all the way? And what's the temperature at the level they're going to be cruising? Maybe if they are in cloud, which they generally are, then they may be picking up icing if the temperature is below freezing. Visible moisture and cold temperatures give us lots of icing. They'll also check the winds as well en route. That plays a factor in the amount of fuel they take and ultimately how long it takes to get to destination. So the weather checks are very important, and they will base their cruise altitude to some extent on what the winds are doing as well. They will take advantage of a strong tailwind if that's the case, or they don't want to be stuck against a strong headwind. After that, they'll check the NOTAMs, or notices to airmen, And these come from the National Air Traffic Service, and that gives the pilot details of anything along the route of flight that's likely to affect the flight. Has a portion of airspace been closed for a particular reason? Indeed, are the red arrows displaying somewhere? Any sort of situation that will call for a reroute or a diversion around that particular area, you will get notices called notices to airmen. Once that's all checked, they will then file a flight plan with air traffic. And they have to file this flight plan at least 60 minutes prior to flight. If it's a commercial operation and it's a scheduled service which has the same flight going same day of the week, same time, for at least 10 occasions, then they can file what we call a repetitive flight plan. And so as the day draws near for the flight, or as the day comes, then that flight plan will be activated. Now in reality, all of this is done by flight operations in a commercial operation, and all of this data is stored in the flight planning computers. So before flight, either operations will get that information for the pilots, and then the pilot's job is to check that information and gross error check it to make sure there aren't any anomalies. One such anomaly may be something like the winds that have been fed into the computer system are 180 degrees out in direction. So therefore that will give an anomaly to the flight time, etc., and the speeds. So it's one of checking that everything's in order. Once the pilots get to the aircraft, they have to check other things such as the weight and balance of the aircraft. How many passengers, baggage, cargo, etc. All that's checked and placed in the aircraft to make sure the aircraft stays in balance. Whilst on the flight deck, the pilots will then look at the performance figures for takeoff and decide what speeds that they will make the takeoff at. Indeed, have they got a long enough runway available for the weight of the aircraft on the day? Then between them, if it's a two-crew operation, they will then do a takeoff brief. And the takeoff brief is basically, so each pilot understands what's going to be happening at each stage of the flight. So for instance, they will discuss the takeoff, the departure, that's the main things they include in their brief, and if there are any anomalies en route that they have to account for. They will also brief for emergency procedures as well. The emergency procedures then, what happens if an engine fails on takeoff? Do they abort the takeoff? Do they continue? So all of that is discussed, and they will then go over the procedures, their emergency procedures that each of them are responsible for. Just prior to pushing back from their parking stand or wherever they are parked, they have to obtain a departure clearance from air traffic control. And that clearance will consist of a standard instrument departure that they have to fly, and doing all their pre-flight checks, they will know roughly which runway they're going to be taking off on because of the wind on the day, and therefore they can expect a departure in a certain direction. And that departure is called a standard instrument departure, or SID. They will also be given a transponder code by air traffic. So at each stage of the flight, their unique code relates to their flight. And they'll also be given any airborne slot time that they have, what time they have to be airborne by. So that's all the pre-flight planning stage. Next stage is taxi and takeoff. They will use their taxi chart, as given in their manuals, for the airfield, and this one is for London Gatwick. So they know where they're parked, and when they obtain, once they've pushed off a stand, started engines, and got their taxi clearance, they can then follow the map to get them to the right runway. So they would be cleared to what we call a specific holding point. And then that's where they would wait to obtain clearance for takeoff. Once they've obtained clearance for takeoff, then they're into flying their standard instrument departure, or SID. And the SIDs, or standard instrument departures, are a published set of tracks, distances and heights that the pilots have to fly in order to get to a specific point. And in this case, this one is for Southampton. The SID, or standard instrument departure, joins the airfield to the airway system. So having flown this standard instrument departure, then they will end up at Southampton, over the beacon at Southampton, the VOR there, and that's where they will start their airways joining procedures. So once they've taken off then, down at the bottom here, it gives them explicit instructions of what to do. And basically what they do is they climb straight ahead on the runway heading, first off, until they reach a mileage of 10 DME, or 10 nautical miles from the beacon at Midhurst. And at that point, they should be at least at 2,000 feet, or 2,500 feet, I think that says. It's a bit blurred, can't quite see it. But not above 4,000 feet. So providing they cross that point at that altitude, all is going well. The next stage then is to fly on till they reach 8 nautical miles from Midhurst. And at that point they have to reach an altitude of 3,000 feet, but not above 4. Then they turn left slightly and head towards Midhurst, the radio beacon at Midhurst on the ground, the VOR. And that is where they have to be at 4,000 feet. After that, they then turn right slightly and head towards Southampton. And then Southampton, from there, air traffic control will give them a climb in order to expedite their climb to their cruise altitude. So the standard instrument departure then joins the airfield to the airways. On this standard instrument departure, that will have been entered into the flight management system of a modern airliner. And once the aircraft is taken off, somewhere in the region about 400 or 500 feet, the pilots will engage the autopilot, and then the autopilot will fly the profile that is depicted there. It knows it from its database. So the pilot's job is one of monitoring, really, and making sure that the autopilot does what has been commanded. The next stage then is the airway, or the airways. So we ended up at Southampton, and going towards Guernsey on a typical flight, they would fly down the airway called Q41. An airway is just like a motorway in the sky. It's 10 nautical miles across, and it's depicted by a track or a radial from Southampton to a specific point, and this point here is called ORTAC. So once the aircraft gets to Southampton, it then again turns left and starts following the airway centreline. The airways are controlled airspace, class alpha, which means there's no VFR flight allowed, so it's all IFR. There are minimum levels on the airway that need to be flown. So in this instance, from Southampton then, they have to fly at least 6,000 feet. That's the base of the airway. Along the airway are reporting points, or waypoints, which are labelled Needle, Camille, etc., Aspen. And these points can either be compulsory reporting points, where the pilots have to report that they're at, or non-compulsory reporting points. Now the triangles that aren't filled in, they're non-compulsory. Also, air traffic can see the aircraft on radar because it's controlled airspace. So if the triangle was filled in, then that would be a compulsory reporting point. Compulsory reporting points then, when they get to them, they need to first of all give their position, that they're at that reporting point, the time that they were at that reporting point, and the flight level they were at, or altitude. And then they would give their estimate for the next compulsory reporting point. So while en route in the cruise, established at their cruise altitude, again, it's one of monitoring the aircraft to make sure that it's flying the route that has been entered into the flight management system. And they will be checking such things en route as their time to the waypoints. Are the times that they calculated correct? If not, is there a strong headwind or a stronger tailwind than forecast? They'll also be checking their fuel remaining as well. So they'll be carrying out time checks, fuel checks. They'll also be keeping good spatial awareness. Although they're under radar control and they can be seen on radar, the pilots themselves listen out on the frequency of the air traffic control that is in charge of that airway, and they will listen for other aircraft. Where are they? They can also see them on a system called TCAS. So very much one of spatial awareness and monitoring during the airway segment. Also en route, they'll be looking to get weather information then for their arrival at their destination. What are the weather conditions looking like at destination? Are we going to expect to hold because the weather conditions are lower than forecast? Or do we have to consider diverting? They will also obtain their arrival clearance in the latter part of the route. When they get down towards Ortac, for example, that's the entry point for controlled airspace in the Channel Islands. So before they reach that point, they will obtain an arrival clearance. And they will be told what approach to expect as well. So therefore, they will both brief for the approach and the landing. So once they get to the point Ortac, which is just here, they then go on to the standard arrival route, or STAR. And this section joins the airway section to the destination airport. And again, it's a set of published tracks and distances and waypoints to achieve. And they will be descended along the arrival route so that they reach their destination at a suitable altitude where they can make the approach from. What normally happens is that although we have these published routes, the air traffic control, because they're under radar control, they may give the pilots headings or vectors to steer in order to prevent the pilots going the full route. So for direct routings, they will give them vectors to where they need to go. And they can keep the aircraft separated while they do that. So the standard arrival route then joins the airways to the destination. So as you can see here from Ortac, if we're going to fly and make an approach, let's say to runway 27 at Guernsey, then we need to fly the arrival route. And that will bring us overhead the airfield, and if we have to hold, into the holding pattern. And this would be a typical holding pattern, and it's just basically flying a racetrack in the sky. It's broken down into three sections, and depending on where you're coming from will depend how you join the hold. So if we were coming down from Ortac into the hold, we'd be coming roughly along this line here to the holding fix. And therefore we can make what's called a direct entry into the hold and take up the racetrack pattern at a specific altitude. Three ways of joining the hold. If we're coming in from this direction, it's a section 1 join, or a sector 1 join, which is called a parallel join. And the parallel join means that we parallel the inbound track of the hold, and then we turn and go back towards the holding fix, and then into the racetrack pattern. If we're coming up from the southwest, then we can do a sector 2 join, or what's called a teardrop or offset entry. So we fly over the holding fix, about 30 degrees removed from the inbound course, for about 1 minute plus or minus wing component, and then we turn right back to the holding fix. So the easiest way to join the hold really is from a direct, or a sector 3, which is a direct routing. So once in the hold, if they're asked to hold, they will take up this racetrack pattern at their holding speed, and also the level that they, or the altitude that they're given by air traffic control, or the approach controller. And then they will be descended, because they'll have other aircraft possibly in the hold above and below them. So as each aircraft descends to the next level, so the aircraft above him will be descended to the next level, until such time they get to the level at which they can start the approach procedure. The approach procedure then, with the holding pattern over the airfield, they can then join the procedure. And this procedure is for a VOR ILS DME for runway 27 at Guernsey. And this gives the pilot a plan view of the procedure and also a profile view of the procedure. So once if he's held in the hold, then as he comes out of the hold, he can then, in this case the hold is actually left-hand turn, he can then go outbound, which is on the inbound course, and do what we call a procedure turn at the end to then re-establish inbound on the final approach track. That procedure starts at a minimum of 2,000 feet. So if he's in the hold, he'll be descended down until he reaches 2,000 feet and then cleared for the approach. Once he's completed the procedure turn, he will then find himself established on the final approach track, and after that he will follow the ILS guidance down to a set minimum altitude, which is depicted at the bottom of the chart. That minimum altitude then is 200 feet above airfield level, or if he's still working from sea level or QNH, then that level, what he needs to see on the altimeter is 534 feet. And at that point, he should be out of cloud and visual with the runway. We also have visibility minimas here, or RVRs, runway RVRs, and that has to be at or above minima as well. So flying the ILS then down to those sort of minimums requires a lot of skill, and once you pop out of cloud, it's very satisfying to see the runway environment where it should be, not off to the left or the right. And these procedures have to be flown within half-scale deflection of the instrument, both glide slope and localizer. So that's taken you through just a brief overview of a flight from a commercial flight from Gatwick to Guernsey. And I hope that's given you some insight into what flying IFR is and how satisfying it can be, like I say, when you pop out of cloud and see the runway straight ahead of you. Okay. Well, thank you very much.